Well, thank you. Hello, everyone. So, as he said, I'm Yoann from Qarnot, and I will be talking about the constraints and challenges of operating a heat reuse HPC cloud platform. Where's the clicker? Yes. Yes. So I'll just very quickly introduce who we are at Qarnot. So Qarnot is first and foremost an HPC cloud service provider. So that's our job. We sell HPC cloud services, and with a value proposition on the low carbon footprint and general environmental performance. And for this, one of the means we have to achieve this low carbon footprint is by capturing and reusing the waste heat from the servers. And because of that, we are also a racks builder and edge data center operator focused on heat reuse. So we build chassis and rack with custom cooling. We install them, distribute them across geographical location. We operate them to offer HPC cloud services, and we reuse and revalue the heat that is generated by the servers. So you have just a small idea of our scale, quite modest for now, but we obviously have ambitions of growing. We were founded in 2010. We are now about 70 employees. We have 70K computing cores. And in 2022, we captured and reused about 2 gigawatt hour of waste heat from the computers. So that's the big picture. A few words on the people here. I myself, I'm Yoann, I'm the team leader, I'm a software engineer, I'm the team leader of the cloud platform team, which is building the core components of our HPC cloud platform. In the room and to talk here, you'll also find Victor, who's the lead of our IT team, Charles, who is a software engineer in the cloud platform team and particularly focused on interacting with hardware and firmwares. And there is also Alexis for a short time with us, who's a hardware engineer and responsible of the team which designs the chassis, so thermals, mechanicals, a bit of electricals too. Some of you may already have met Clément, our CTO, but he's currently not available. And other people also may know Paul, who's our founder and CEO. Okay, so let's see what focusing on heat reuse shapes what we do, and then we'll see what implications it has on what we need from the hardware we operate. So to reuse heat, we have to capture valuable heat. It means extract as much energy as possible and as hot as possible. We need to do that where the heat is needed, and as much as possible to ease integration, we have to use existing infrastructures. So existing heating facilities and existing buildings as much as possible. What does that mean? Capture valuable heat using existing infrastructure. We have to be very efficient in the heat that we get. We are proud to capture and reuse up to 95% of the heat. So 95% of the electricity that comes in the system gets reused as heat in a heating network. It's very important for us because every percent of heat we get is heat we can sell and reuse. It needs to be very hot. It might sound a bit silly to say, but the hotter it is, the most value it has. Heat at 40 degrees has less value than heat at 60 degrees. Sometimes it's even a regulation thing. Domestic hot water has to be heated at more than 60 degrees. It's regulatory. Otherwise, it cannot be domestic hot water. And we want to reuse existing infrastructure, so we have to operate on tap water. Nothing fancy, no ultra pure water, no specific cooling fluids. We just want normal tap water. And we want our plumbing to be operatable by plumber. One of the requirements is that when a plumber in a normal heating room sees this computing unit, they say, yes, that looks familiar, I know what to do with that. They won't know what to do with the computing, but they will know what to do with the plumbing. They are not DC operators, they're just plumbers who do heating stuff. So all this means that it led us to design our custom racks and custom cooling for the motherboards. Another thing is that we want to use heat where it's needed using existing infrastructure. Nobody, or almost nobody, needs a gigawatt of heat at 65 degrees at all time in the year. It doesn't exist, or maybe, but it's very niche. Many people need half a megawatt or a few megawatts of heat at 65 degrees. So it means that we have to deploy in small units. And if we deploy in small units and want to scale, we need lots of units. So we'll have lots and lots of geographical locations where we will be deployed. So to sum it up, we want carbon efficiency, so we want to reuse the heat. And it has implications that we design our own cooling and we will be geographically distributed. So now let's see what this has impacts on the hardware that we want to operate. So let's start by so the impact on the hardware, and let's start with what custom cooling means. Custom cooling, designing our own cooling, means that we need to know exactly what needs to be cooled and by how much it needs to be cooled. It means that we are going to strip down vendor cooling and replace it because we do our own cold plates and replace all the vendor cooling for efficiency purposes. And it also needs that we want high temperature components because, as I said, the hotter we can get, the most value it has for us. So knowing what to cool and by how much, what does it mean? It means that we'd like precise schematics of the motherboards, like OCP gives us, for instance. We need to know exactly where everything that needs to be cooled is placed. And we need the thermal requirements of everything. How hot can it operate, and how much heat is the component going to generate, so that we can cool it down properly. It's thermal, but it's also mechanical. We have recently introduced a new motherboard, and we discovered that we have to apply much more pressure on the CPU, between the CPU and the heatsink, than we were used to do. And this is going to need us to rethink a bit of the mechanics of everything. So we also need to know these kind of things. Usually, you just buy the hardware and the normal cooling system, and you plug it, and everything is pre-designed. But we are going to replace that, so we need to know the what needs to be applied as mechanical. And also what we like about the hardware is that the stable must be designed. It's a bit like Anis said before. What is equivalent for you might not be equivalent for us. If you move between revisions, if there is a chip that is moved 5 millimeters to the right, then we have to redesign the cold plate. It's a lot of money, and it's time to market that we waste. And so the point here is that we would like to know this as early on possible in the process. We can do all this by buying a motherboard and measuring. We can do trial and errors on the cooling. We already did it, but it wastes time. If we can know all this early on, we can make our designs earlier. It improves the time to market of the hardware, and so the time to market of our cloud services. So it's more value for us. And also, if we know everything in advance, we can make more reflected decisions, and so it's better TCO in the long run. Custom cooling also means that we will remove all the vendor cooling. So taking it apart should be easy. We love the OCP way of touch the green. You want to take something apart, find the green stuff, pull on it, comes apart. It's just great. Even better, we don't want the cooling from the vendor because we're going to remove it anyway. If we get it, it's manpower time to remove it, it's cost. It's some hardware that we'll have to dispose of, so it's cost and also wasted resources for the environment. And we don't like that. And most importantly, removing the vendor cooling stuff should not void the warranty. There is currently on the market some pieces of hardware costing about $40K a piece, which warranty gets voided if you remove the vendor cooling. It's mostly a no-go for us, or at least it's lots and lots of friction. So please don't do that. Also, as I said, warmer is more valuable. So we need high temperature CPUs with high TKs. It's, for many people, the TKs of the CPU is just a data. For us, it's a choice criteria. And we need all other components too to be able to live in the heat. We're very happy to pay a bit more for components that can sustain 90 degrees and not 60, for instance. Here it's a bit specific to us because we want to reuse the heat, but it's not just us, because any traditional DC would benefit from this, because going hotter means that you can do free cooling. If you can cool things at 60 degrees, you can just have free cooling, no AC, so very good PUE, and no adiabatic cooling, so no wasted water. So it's a specificity we have, but I think it's actually everyone's. So now let's see some of the challenges, not from heat reuse, but from geographical distribution. Traditional DC operators, the small and medium people will have tens of DCs, the big shots will have hundreds, maybe the hyperscalers will have thousands of them. When you operate edge DCs, we already have tens of them, soon we'll have hundreds. In a few years we might have thousands or tens of thousands. You don't manage this the same way as a few tens of data centers. Once again, it's not just us. We do it because we want to reuse heat, but edge computing is a trend that is not just us. So small and medium actors already have or will have thousands of data centers to manage. And this creates, as every scale, it creates challenges due to the scale. So one of the things is that physical is that intervention is not an option for us. If we have hundreds or thousands of facilities, pushing a button is extremely costly. It's distributed across France and Europe. Pushing a button might be a full day of work of a human. So it can be very expensive. It also means that firmware upgrades, firmware in general, the hardware in general, but in particular firmware upgrades must be rock solid. It's impossible that we can break a data center that is 500 kilometers away just because of a wrong firmware upgrade. So it must be fully remote, it must work, and it must be forgiving. If by mistake I flash the wrong thing, I need a remote solution to roll back and get it back to working. It's true for the BMC, for the BIOS, for the NICs, for every firmware in the server. And once again, it's not just us. For us, it's very costly to push one button. For everyone, it's very costly to push 10,000 buttons, even if it's in a single facility. Another challenge that we have with geographical distribution and deploying very small units is that we have our physical security has various grades. We deploy in existing sites, sometimes very small, so that the physical, buying very high-end physical security is not economically viable. As we'll use existing facilities, so sometimes we cannot just retrofit the physical security of a normal data center. And sometimes we will have, by design, to share the facility and share the access with the heating people. We try not to as much as possible, but sometimes we have to. So we have varying levels of physical security. So we are able to sell different levels of physical security, but as much as possible, we like to compensate this with logical security. What do I mean by logical security? First and foremost, something like TPM remote attestation. Something that can give us trust in the fact that this hardware is our hardware, and this firmware is our firmware, and it has the right configuration, the one that we want. I say TPM remote attestation. It can be something else than TPM. Actually, TPM does lots of stuff. We are mostly only interested in the remote attestation part. But why remote? Because we want to take all the decision outside of the host hardware. We don't want to brick a hardware or have to physically intervene on it. So we want the server to say, I'm this, trust me or trust me not. Then we take the decision, but outside of it. And a very important thing is that it has to be stable and predictable. There is not one configuration that we will accept for a server, maybe 2, 10s, hundreds, because we allow several configurations, several versions of the firmwares, maybe some cable plugged in or not plugged in. Maybe it matters, maybe it doesn't. We don't want to reject the server for that. So we have to be able to take all those configurations and pre-compute offline what it's going to do to the PCRs. And then we can whitelist those configurations and say, okay, it's in this configuration, fine, I'll keep it. And then you can also handle the end of life of your firmwares and just accept some things, but raise a warning saying, okay, this server has this configuration, it's okay for now, but you have to do something about it. So it's the traditional workflow with this, which is boot it, look at the PCR, seal things, and now accept that. It's not very nice for us to have, and I guess for everyone, because it's very important for us because we have varying physical security, but I think every operator does like to have the additional logical security, whatever happens. And I see this as a very big challenge in management to do it at scale. At least that's what we see, because we really had lots of difficulties to implement this. So for now, I've shown things that are mostly specific to us, or not entirely, but mostly specific to us because we do heat reuse and because we do small data centers. But we're also mostly normal people, and you will find in the next slides many things that Anis just talked about 10 minutes ago, so sorry for the repeat, but they say that pedagogy is about repeating, so let's do that. So yes, we do weird stuff. We strip down the servers, we do our own cooling, we integrate with unusual heating systems and deploy in unusual places. But at the end of the day, we're just an HDC operator selling cloud HPC services. And so the challenge is the same as everyone. Make the server works and make them work at scale. So a bit random things about all it needs, and you'll see. You've already heard about that. Support. We are engineers. We like to talk to engineers. When we hit problems, it's complex problems, because the simple problems we just can solve ourselves. I promise that it's not a collusion with Anis, but yes, we did try to turn it off and on again. We do that. As a side note, if we need to turn it off and on, it's a problem in itself. But we did try. And we know how to produce valuable bug reports, make experiments, and try to reproduce stuff. We can give this value to you, those valuable bug reports. This is mostly important during the bring-up phases when we try to integrate new hardware. That's when we are going to face the problems, mostly. It can also be useful after some firmware upgrades if something goes south, but mostly during bring-up. As software engineer, we can read, write, and debug code. So if the firmwares are open source, maybe we don't need to talk to support. Maybe we can just look at the stuff, fix it, make a pull request, and then it's fine. It's even easier for us if everything is based on Linux, because we know what Linux is, we know how to develop and deploy stuff in Linux. So OpenBMC and Core Boot just look great for us. One very important thing is that you must not forget the tooling with it. Having the code is great. Building and deploying the code is better, because code that we can't build and can't deploy, it's pretty useless. We're a cloud service provider, not like Criteo before. Criteo, they have their own applications, and so they know what hardware they want, so they will want a few variations of the servers, but not lots of variations. We have customers. Customers want different things because they have different needs. So we have to offer a big diversity of hardware. Big diversity means issues in manageability. So for manageability, we need to bring back Unity as low as possible in the stack. And as low as possible needs BMC, firmware, Core Boot, everything. And as Anis said, Redfish is not enough. Redfish has way too much diversity. Redfish is a framework, it's not a spec. So once again, OpenBMC, core boot looks like a very good idea. On the hardware part, we start seeing modular BMCs, swappable modules. It's nice because we can pick the one we want. We also start hearing about PXE bootable BMCs. That looks just wonderful because if we can boot the same PXE, the same BMC firmware everywhere using PXE, it's just great. So make this work at scale. As software engineers, we like APIs. Anis already said that. It's 2024, HTTP APIs are everywhere. It's the ubiquitous, universal building block that you can use to integrate with any tool. So if management interfaces are API first, we will love it. It will make a big difference for us. And importantly, as software engineers, we're used to write, build, and deploy software at scale. You might have noticed in the presentation slide, we are mostly all software engineers here at Qarnot. We are the software engineers deploying and managing the hardware. So firmware should be no different from the rest of the software. If it's open source with tooling, we can build it with our usual CI. If there is the tooling and deployment tooling, we can deploy it with our CD. We want CI/CD from firmware. Managing a server fleet is a DevOps job. It should be doable with DevOps tools and DevOps flow. The take is that firmware should be just one more piece of code in the stack, no different from any other piece of code. And that would really help us manage everything at scale. And I guess it's what the hyperscalers do. And we are not hyperscalers, but we're still scalers. As a cloud service provider, we don't like downtime. I think Anis also talked about this, but as much as possible has to be done out of bound and without downtime. I understand that it's not always possible, but as much as possible, it's nice. Managing rolling downtime is a bit of a pain when you operate your own application. It's a much bigger pain when you operate other people's applications. The long server life, it was already talked about in the talk and in the questions. We think for our hardware for 10 years, not 3 years. So we need to have long-term firmware upgrades. We need to be able to apply security patches in the firmware for 10 years, 12 years, maybe more. If it's open source, we are very happy to help maintain it. If it's not, we can't. And all the crypto stuff needs to be upgradable too. In particular, the crypto chips. What a shame it is to have to decommission a $2,000 server just because a $10 chip has SHA-1 hard-coded in it. That's really a shame, isn't it? TPM 1.1, for instance. And as rational actors, we think in terms of TCO. We are very happy to pay a bit more upfront for the hardware. We're very happy, well, happy, I won't say happy, but we are ready to pay a bit more for the hardware, and I didn't write it, but also for support, as was discussed before. If we can get the money back, we can get the money back with integration cost, with day-to-day operational cost, and with long-term operational cost, increased lifetime. This is getting us the money back, so we can share what we get on this money, a bit for you, a bit for us. Not everything for you. And some other important thing, as original people, it's likely that we're going to want things that you didn't think about. Actually, it's likely that we are going to want things that we didn't think about. Tomorrow, next week, next month, we'll want things from the hardware, firmware that I have no idea about it today. And once again, if everything is open source and customizable, we can just do it ourselves. And it's an enormous value for us. It's an insurance on the future. If we have the firmware and the tooling to do it, we can just make things evolve in the directions that we want. And those directions might be specific to us or might be not specific to us, might be shared with lots of people in this room and outside this room. So that's another thing for open source firmwares. So calls to action, which is borrowed from the OCP style conferences. I'll summarize it as one thing, and it won't be a surprise. Let's build around open source firmware. And let's make firmware just another piece of code in the stack. I just want this firmware to be something in my GitLab and built and deploy with GitLab CI, just like the rest. That's it for the rants. So thank you very much for listening. If you want, thank you. So if you want to talk to us, on the left, people who are here today. On the right, people you can contact. You can privilege Clement or CTO, but you can also put me in copy if you want fast feedback, because he's currently not available. Thank you.
I have a question about your activity. When I was a student, something like 25 years ago, we had a project with a friend which consisted in doing exactly this. I mean, collecting heat from servers and reselling it for people to heat their house, for example. And we figured that nobody's interested in heat in summer. And we thought that maybe it could work in northern countries or southern countries, but only half of the time. So we could not move servers, or we would have to have the double number of servers. And I'm curious to know how you solve this.
Well, actually, people do need heat in the summer. Less, that's true. We won't ever provide all the heat in the world because winter, right? In winter, you need much more heat. But in the summer, I don't think you shower on cold,
Almost.
almost. Well, not everyone showers on on cold water in the summer. There are industrial applications who need heat all year long. So heating systems operate at a lower scale in summer, but not zero. And so what we do with our deployments is that we take this low point and we deploy this capacity. And then we are supplemented by traditional, like gas or more electrics or anything for the peak demands. And what you can see when you look at the usages is that even deploying this small power, it will provide a much higher percentage of the year-long capacity. So you deploy 10% of the power and you provide 50% of the energy, for instance. It's not the right figure, just don't take it as granted, but it's an example. It does work better in northern countries, but not specifically because of the summer problem, but mostly because they have a culture of the heating networks much more than in other places. So the Nordics are a really great target for us because they have heating networks everywhere.
Okay, so you never have to reduce your server capacity, for example, just to accommodate less demand?
We size the heating sites so that we don't have to do that.
Okay.
To be able to privilege the HPC customers. Because we are focused on HPC. So HPC means that we cannot just throttle down stuff because customers won't be happy about that. At the very first start of Qarnot, we didn't do the heat reuse with water. We did it directly with air and with domestic heating systems. And we did throttle the CPUs to consume less energy, but we don't do that anymore.
Okay, thank you very much.
Well, hello. Thank you for your presentation. So I just wanted to ask you a question regarding OCP standards and technology regarding the edge data center. How do you think this form factor and technology can help you minimize the downtime and provide you with a more reliable overall solution?
Well, actually, we're not focused on edge because we wanted to be focused on edge because we need it for heat reuse. Concerning the hardware itself, we are focused on HPC. So our first criteria is the performance and how it is viable for HPC customers. We'll talk a bit about it in the roundtable about densification. I guess because having very dense machines is nice, but it also means that it fails very big chunks at a time, which can be a problem for us. I don't know if that really answers the question. Or
Partly, yes. I just wanted to know if, well, for your core data center solutions, OCP is clearly your technology of choice.
yes.
But for edge applications and computing projects, would you consider OCP as well, or would you switch to standard 19 inches servers?
Actually, we do OCP not specifically because of the form factor, but because of the openness of the thing, because we have the schematics, because it's very handy to use. If we can have that from something that is not OCP, we're not close to the idea. What we need is that it can easily fit in one of our units, so that we can design the cold plate easily. Anything that is easier to cool down with a cold plate is a win for us, OCP or not OCP.
You've been speaking a lot about open source firmwares. Do you have experience with them? Did you try them? And even better, did you deploy them in production?
We are currently having an experience with them. We tried to build and deploy OpenBMC on Tioga Pass or OCP servers. It's not been a very smooth process, I have to say. We've had lots of difficulties building it, then deploying it, then seeing that it doesn't work, changing the build flags and deploying it again and again and again and again. And I think we are not yet there. If you want a hands-on experience of this, you can talk with Charles afterwards. He's the one taking care of all this right now. Well, not right now, but...
Hi. Yeah, thanks for the talk. I basically had the same question around open source firmware. We got it running on the Tioga Pass, OpenBMC, so if you need help, you can reach out to us and we can talk about it.
Great.
Yeah, and I was more also interested in the other stacks, if you have that, if you have any experience with that, or if, you know, how the transition goes, but you basically answered that already, right?
With what? Sorry, with?
With the other firmware stacks like core boot, host firmware, right? So you're looking at BMC specifically right now.
Yes.
You said you're also interested in host firmware. Are you also looking at, for example, root of trust firmware as well?
So we're currently focusing on BMCs because it's the most urgent, I would say. It's the interaction that we have every few seconds with the server. So it's very important for the BMCs. But we are also very interested in core boot, but we never had the bandwidth to to try that yet. But it also looks like a really great thing. We start having question and manageability question about configuring the BIOS and upgrading the BIOS, changing the configurations of the BIOS and deploying all this. And I guess, but it's just a guess, that core boot would help us a lot with that. Also to deploy, to build and deploy custom modules in it. It's just, well, just Linux, right? So we know how to handle that. Well, it's a weird Linux, but...
Yeah, thank you.
Yeah, much more fun.
I have a question. You said you had a lot of constraints with the motherboard and you don't want parts to change because of the way you're designing the cold plate. How far are you to designing your own motherboards as well so that they fit all your needs, whether on components or placement?
That might be a long-term goal, but designing a motherboard is a very, very complex and huge process. So we are very far from it yet. We don't have the scale. We don't have the scale in many ways. We don't have enough people to do it, and we wouldn't produce enough of them for it to be economically viable. Yeah. So maybe a day, maybe someday, but in many years, I think. And I'm not even sure if it's worth designing our own stuff. I mean, even the hyperscalers are mostly sharing things with OCP. If they feel the need that they can share things, maybe it's a hint that we shouldn't do it on our own.
Yeah, thank you.
Do you think that DC SHM design can be an answer to your needs? For example, having some modules, modular server, and each module will respect some standardized measure, and but let's say standardized, even if it's an Intel, or Dell, or any manufacturer, can be an answer for you to changing less the design of the plate, for example?
Yes, definitely. Everything that is more standard and more stable across time and more predictable is a win for us.
Earlier you said that the hotter the better. So
Yes.
We, Dell, and our friends at Intel and AMD, we are very happy to see at least somebody who is happy with the TDP chart.
It's not actually the TDP, it's really the temperature.
So
It's the TKs. To 200 watts, but with a TKs of 50 degrees, it's not interesting for us.
Yeah, you want the hot.
Yes.
90 degrees is better for that.
Exactly. Yeah.
How dense can you get? Because you said that you mostly focus on edge, but how dense can you get with this design, and how dense do you project to be in the next years?
Well, I couldn't answer with figures with that. Mostly, the denser we can get, the best it is. But then it still has to be manageable to cool it down. So lots and lots of watts on a very small space. It's a very big challenge. The cold plates have their limits. We try to improve the designs of the cold plates by various means. But at some point, when we see, for instance, the MI300, it's like, I don't know, maybe 600 or 800 watts.
750.
Yeah, 750 on something that is not very much bigger than a Genoa CPU. It's very interesting. Interesting challenge. It's a very nice challenge. If we manage to extract all this heat, if it goes to 90 degrees and we manage to extract all this heat, it's a very big win for us. But challenge. Yeah,
Okay.
Definitely.
Thank you.
Did you try to push the components beyond the specs? I mean, maybe you have some feedback, like the CPU dies after 5 years or something like this, but for your use case, possibly you don't care if it dies after 5 years.
Yes, we definitely push them beyond the specs, sometimes willfully, sometimes by mistake.
For sure.
The problem is that we don't have the specs of everything, and sometimes we discover things along the way. But sometimes we just didn't look at it properly. Sometimes we don't have the data. We already had occasions where we discovered that our network interfaces didn't work properly at the heat levels that we put, so we had to redesign the cold plate to also cool down the NIC. And we also had to change the SFPs because for hot ones, that was just a silly mistake from us. But yes, we did try. Sometimes it works, sometimes it doesn't. What is quite nice to see is that even though we don't have very specific studies about it, it doesn't seem that we have hardware dying earlier because of the heat. So when we have a working design, something that is stable, usually it stays stable, which is very nice to see because we didn't really know in advance.
I'm not surprised. It was also my experience. What I noticed the most was dying capacitors on motherboard, in fact.
Yes, I don't think we have too much of that.
You mentioned the fact that you would like to have some, at some point, I would say, or being able to update firmware without any downtime. Did
Yes.
you study it with several companies? Do you know how many people or companies are interested by such feature? I'm mentioning because, in fact, I'm working on this kind of project since 3 years. We are, I would say, trying. We have difficulties to have, I would say, some traction in the, I would say, server manufacturer ecosystem. So if the demand comes from the end customers, that would be nice to have some discussion about it.
Okay, noted. We are in the early years of managing BMCs. Actually, we started with end users motherboard which don't have BMC. And it's been a few years since we started working with proper BMCs. So we took the fast route to get it on the market. And now we are starting to really think about the big challenges about it. But it's very interesting to know that you work on that.
Good.
Hi. We're using Sonic switches for Tor. And do you intend to work also on switches?
It's something that we will do in the future, most probably. Currently, we don't use Sonic switches. We have some wedges with WedgeOS, I think. I'm not entirely sure of everything we have. We didn't work a lot on the network, but it's definitely something that we will explore more in the coming years. Right now, we just take off-the-shelf stuff that works. But it's true, everything that I've said about firmwares and BMC and stuff, it's also true about the network equipment. It will be a focus for us in the coming years. Good point.
So thank you for the impressive presentation. So I strongly resonate with your point about the firmware and then everything, like the long-term maintenance is a pain point. It's a really huge pain point. Because we see that for decades, many hardware vendors or the data center customer, they don't have the control on their own firmware at their hand, so they have to rely on third parties and to do the updates and stuff for them. And then every time the third parties, they abandon them after 5 years or even 3 years of work. So I definitely see a huge demand on this. And then OpenBMC, like you said, is a first step for the revolution to begin, because you can start from the small stuff, from the BMC first, to control for the whole firmware stack. And then the host firmware, we believe, will be the next component that will start the trend. So I think it is a trend that's begun, and then especially for us, we have built the framework with the silicon vendors like Intel, AMD, Ampere, and to start to build the framework for the next decade of the firmware, open source firmware. So that's why I see that this is a really good point that we are all going to. Thank you.
I think everyone has to benefit for it. Also the vendors and also the manufacturers. I think like OpenBMC and Coreboot are today's Linux from maybe 20 years ago. You used to have every mainframe vendor building their own OS for it, and now you have Linux everywhere. I hope that the trend is that we have every vendor building their firmwares, and in a few years there will be OpenBMC and Coreboot everywhere. Same path, same, yeah.
Yes.
I hope.
Thank you.
One last question, maybe?
So thank you.
Well, thank you.